Okay, this problem asks us to show the following with two parts. It says let D be an integral domain and suppose F is a field with F a subring of D. Show that D is a vector space over F, and then part B is if D is a finite dimensional vector space over F, then show that D must not just be an integral domain, but actually a field. Okay. So let's start with part A. So we want to show that D is a vector space over F. Um, so a vector space is a module over a field. So we need to check that D is an F module. So check D is an F module. So uh, we have a ring action, right? So we have map from F cross D to D. And the map is going to be uh, the expected thing, which is just multiplication in D. Uh, so let's check the modular axiom. So let R and S be in F, and let X and Y be elements of D. So then what's the first one? We need R x plus y equal Rx plus Ry. Well, certainly this is true because F is a subring of D, and D is a integral domain, or in particular a ring, so the distributive uh, law holds, where we're just taking the action to be multiplication in D. Okay, so that's good. Um, Similarly, we have R plus S acting on X. Well, what's that going to be? Well, again, by the uh, right distributive law this time, we have Rx plus Sx. So distributive laws of the ring D. Okay, what else? Well, Rs acting on X, is that going to be R times Sx? Yes, it will be. Associativity of multiplication in our ring tells us that. Um, and then the last thing we need to check is that uh, 1f acting on x gives us x for all x in D. And this one is usually the simplest thing to check, but in this case it's a little bit non-trivial because we don't know that the one of our subring F is necessarily the same as the multiplicative identity of our integral domain D. In general, a subring of a ring uh, need not have the same multiplicative identity. For instance, if we looked at Z mod 6Z, uh, and its subring uh, consisting of the elements 0 and 3. Well, then 3 is a multiplicative identity of this subring, right? So, even if we're requiring our subrings to have a multiplicative identity, which we are here, it doesn't need to be the case that the subring's multiplicative identity is the same as the rings. But nevertheless, this is true for an integral domain. So let's have as a lemma to get that last criteria. So let R be an integral domain and S be a subring of R, then the multiplicative identity of R is equal to the multiplicative identity of S. Okay, and let's prove that. So suppose not. Well, then when we subtract 1R minus 1S, we don't get 0. So 1S times 1R minus 1S is equal to, well, by the distributive law in R, 1R times 1S is going to be 1S because 1R is the multiplicative identity for all of R. So 1S. And then 1S times 1S will be 1S. So this will be 0. Um, but what does this mean? Now, 1S is not 0 because it's integral. Um, right, we're, integral domain, we have uh, 1 not equal to 0, and to be a subring, we need um, 1 not equal to 0. So R has now non-zero, zero divisors, right? Because we have 1S times 1R minus 1S, both of which are non-zero, um, that multiply to 0, contradicting that R is an integral domain. Um, okay, so we're good on this last point. Um, that 1F times X is equal to X because 1F is actually 1D, so that is going to hold. All right, so that completes part A. So now let's move on to part B, which says that if the dimension of D as a vector space over F is finite, then D is actually a field. So let's show that. So to show that D is a field, we'll show that any non-zero element has an inverse, a multiplicative inverse. So let's let D be an element of D with D non-zero. So we want to show that D has a multiplicative inverse. Um, well, one thing we know is that since the dimension of D as a vector space over F is finite, um, uh, um, the infinite list of elements 1, D, D squared, D cubed, and so on. This must be uh, this infinite list must be linearly dependent over F. And I mean, if this list is not actually infinite, then um, since we're working in integral domain here, one of these um, powers of D must actually be one, in which case D is already invertible, so we're done. So um, okay, so this is the only interesting case. Um, so these are linearly dependent, and moreover, there has to be some, the dimension's finite, so there has to be some finite number of these elements that is also linearly dependent. And there exists some minimal number that is linearly dependent. So there exists some natural number m such that 1d squared to d to the m is linearly dependent over f, and um, m is less than n for any other natural number n with 1d squared d to the n linearly dependent. Okay, so we have some minimal power m such that 1 to d to the m are linearly dependent. And what does it mean for them to be linearly dependent? Well, that means that there exists a 0 to a m elements of f, not all 0, such that a 0 plus a1d plus a squared d, or a2d squared plus am e to the m is equal to 0. Um, so now let's claim that a0 is not 0. So suppose a0 equals 0. Then what can we do? We can refactor everything else as d times a1 plus um, a2d plus a m d to the m minus 1, which is equal to 0. And since d was non-zero by assumption, and capital D is an integral domain, well, that means that a1 plus a2d plus am d to the m minus 1 is equal to 0. And now that contradicts the fact that m was the uh, least power of d, such that 1d squared to d to the m um, were linearly d um, pendant. So uh, contradicting minimality of m. Okay, so that was all under the hypothesis that a0 is equal to 0. So a0 is not 0. All right, so a0 is not equal to 0. And, well, what does that mean? Thus, a1 d plus a2 d squared plus am d to the m is equal to negative a0. And remember, all these a's are elements um, of our field, which is a subring f. So factoring, we get D A1 plus A2 D plus plus AM D to the M minus 1 is equal to negative A0. Okay, so since A0 or negative A0 is also an element of F, there exists some B um, in F, and then there's also in D, such that negative A0 times B is equal to 1. Our 1 is unambiguous by what we said earlier. So um, then, if we multiply on the right by B, we can also multiply on the left by B and get 1. So what does that mean? Well, just, you know, by the associativity of multiplication, that means that D times A1 plus A2D plus AM D to the M minus 1, that element times B is some other element, and D times that element has to give us 1. So D is invertible, and D was an arbitrary non-zero element. Thus, D, which was an integral domain by hypothesis, must actually be a field. And that completes part B.